Welcome back, robot guys! I've been designing mechanical systems for a long time, and usually when something looks right, it probably is. What I've done up to this point is when I don't know which components to use, I've looked at what other teams are using and I've followed their example on what components to use internally on the robot, or I've just made a logical judgment. People call this a gut feeling or intuition, but what it really is calling on your experience from just being around stuff that you've seen work and fail previously. That's not really an option with this brushless drive because few people use it, so there's not many instances where it's worked successfully. I've had another look into motor theory and I think I know where I went wrong. I was using the stall torque and the startup torque interchangeably, and I don't think that this can be done. The startup torque is the torque the motor needs to spin from a dead stop, and the stall torque is the torque that is required to stop the motor once it's already spinning. I'm sure there are people watching this that have got a much better grasp on this and they're just screaming at me and I'm missing so many obvious things. I don't claim to be an expert on all things, and there's many aspects of robot building where I'm just figuring it out. We're still learning here. When I first started doing this around 2 years ago, I barely even knew how to solder. I had to learn lots of new skills. I do have a little bit of a better understanding of the theory now, but I'm not going to say it's enough to rely on for this. Also, to implement the theory, you're still relying on the manufacturer spec, and I stand by what I say where they are biased and they're trying to sell you something, so I wouldn't trust that anyway. I mean, it's certainly a starting point, but I still... So how do I prove something's going to work theoretically when I don't know the theory? I bought a bunch of the brushless motors to test against the amp flows. This still doesn't mean that we've made up our mind that we're going to use these. These are the larger Maytech motors that there's a lot of interest in at the moment. They are a pain in the neck to import. You have to pay a bunch of shipping, you have to pay again once they get to the border because you have to pay all the import fees, and the lead time is long as well. They take ages to get here. I figure if we decide they're not for us and we decide not to use them, we can just resell them because there is demand for them. We will review some of them. I'll lose some money, but it's not as big a risk as it sounds. So what I'm going to do today is unbox them. We can take a look at them and see how they work and how they go together. Then I'll take some dimensions and I'll walk through the process of getting them onto CAD. So I'll be using SolidWorks. I'll do this for the motors and for the gearbox, and depending on the length, it might be 2 videos. Let's have a first look out of the box at the Maytech brushless motors. So the first thing you may notice is that there's 4 wires coming out of here instead of the regular 3. So brushless motors are 3-phase, and what they rely on is each of these are kind of pulsed with power to get the motor to spin. It changes the magnetic field inside the motor and gets this to spin. What this does here is there's a little sensor in here, so it's a little, I think it's a Hall effect sensor, and it gives some feedback so it knows which ones of these to phase. I've kind of been led to believe that that's the secret to keeping these things working under high torque and low RPMs. Brushless motors, obviously, they usually work under low torque and very high speed. So the usual use for something like this is a hobby airplane, or they've been used recently in skateboards. This is an outrunner, so this can here, this outside shaft, this outside can spins with the shaft, so it's fixed at a point here at the back, and it's mounted on this front face, and this whole thing turns. So it does make mounting these a little bit difficult because you have to obviously pick up on this front face and you can't hold the can, so there's quite a lot of weight on the back. So my first impression of these is they seem like they're really well made. They're really, the machining on it seems really nice. So this one here is I think this is aluminium on here. It looks like it's made from a solid piece of billet. Yeah, so that's aluminium. I'm not quite sure what the surface finish is. It's probably just some sort of anodization. Yeah, so it's not too deep, so it's probably just an anodized. It's a little bit shiny as well. It kind of gives a bluish tint on it that you can't really pick up on the camera. Focus. And then this outer body is steel of some sort. And it's a sealed unit as well, so there's no, the only space anything can get into the unit is this little gap there between the mount face here and this can. This back face is all sealed up, so you won't get little bits of swarf in there, so it's pretty good for, this is obviously a skateboard one, so it's meant for off-road usually. But that suits our purposes because we don't want little bits of swarf and dirt getting in there where it's whipping around an arena. So these are all metric dimensions, which is nice. So we're looking at a 8mm shaft and a 3mm keyway, which is quite cool. I don't really like keys because you need to get them very, very precise, otherwise they kind of roll over and they round out the, eventually they take the edges off and they do end up moving, especially if you're going backwards and forwards a lot under a lot of torque, which we will be. So I'm not really too keen on keyways, but it's fine. There's little circlip grooves here as well on the top and bottom just to keep the keyway or whatever you put on the top to transfer your energy. So if it's a gear or a pinion or a pulley, it keeps it from riding either too low or pulling off altogether. I really like circlips as well. I've never seen a circlip fail, as long as it's been installed correctly. I've never seen one fail in normal operation in my entire engineering career. It's never the circlip that fails, it's something else. 12 American wire gauge wires, and I think they're 8mm bullet connectors on there. And they're silicone wires as well, so they should be pretty good at wicking away the heat. What's this shaft made of? Yeah, so some kind of steel shaft. I thought it might be stainless. It's very, very shiny. A little bit of burring on the machining for the keyway. Focus. Come on, you can do it. Yeah, a little bit sloppy machining, but... So this body is fixed to the shaft. It goes all the way through this mount face here, and there'll be a sort of stator unit that goes all the way through, and there'll be a bearing at the back on this shaft and a little bearing on the front. And it really is a tiny little bearing in there. So it's a 1980 KK, which I think means sealed on both sides, and it is a NMB. Which is it's a brand made in Thailand, and that's a decent brand of bearing. But the bearing here, this is tiny. If you imagine how big the ball bearings are going to be in there, they are very, very small. And we're asking them to do, I think it was over 8,000 RPM we calculated last time. We're asking them ball bearings to take an awful lot of force, especially if you're trying to preload this. So by the time you put if you used to put a V-belt or something on there and you need to load it, you're really, really putting a lot of stress on these bearings. So that would be my only concern, is that these are probably a little bit small for their application. Another point of failure that might occur is the way this shaft is attached to this can. So it's probably just pressed in here into this housing, and then it's got a tiny little grub screw. It's got two little grub screws on there. So they're probably M3. Yeah, so it's got two little M3 grub screws just to try and retain the shaft and stop it from turning. So if we're putting an awful lot of effort into this end to key our gears on, and then that becomes a very, very strong union there, and the gear isn't going to slip on the shaft. The shaft in turn will then slip on the housing. So this will just start this will just start spinning in there if this gets up to enough torque, and if especially if we're doing lots of backs and forwards. So I might be a little bit concerned about that. We've got these are obviously the mount holes there, and they go pretty deep, so about, yeah, maybe 6mm or so deep. I'll have a look when they get it off, but are they at M4 again? Yeah, M4s. So as a general rule of thumb, in aluminium, I try and go 2 times the diameter of the bolt when we're tapping into aluminium. So we want to see about 8mm there. So if we're about 6 or 7, that's okay. And it's got 2 sets on there, which is quite nice. You probably won't be able to get 8 bolts in there at one time. You have to choose either the inner diameter or the outer diameter, because obviously the heads will clash. But it's nice that you have some options just in case you ever do wear these holes out. This obviously is going to be very difficult to replace. It might actually be possible to tap these out to a larger size, but then you won't have a lot of depth engagement with the bolt, so I probably won't end up doing that. Right, let's take it apart then. I think it's only retained by this little circlip in here, so it's a little 8mm circlip. You want to squeeze this just enough that it has room to get off the shaft. You don't want to go and open this up really wide, because you end up, you take the circlip past this elastic limit, and it then won't go back to size again, so you have to replace it. And that's one of the ways that the circlips do fail, is installation error. Cool. That's just the circlip. And what we got is just a couple of shim washers on there. You can see they are actually different sizes, they're different thicknesses. So what they do is they use these shim washers just to make sure that the edge of the shoulder for the circlip groove is butted up against the inside ring of the ball bearing there, just to make sure there isn't too much play in and out. So the only thing holding this motor on now is the force of the magnets. If you're doing a bunch of these at one time, if you're taking a bunch of them apart, you'll want to keep these shim washers with this motor. They will be specific. And then what we're going to do is just, you grab this end, and you grab the can, and you kind of just...
Like crazy.
So yeah, it did need a little bit of a wiggle, so you notice these bearings, they kind of get caught on the shaft. They get caught on the little grooves in there. And they also kind of crab up where they've got a little, all the bearings have a little bit of floating. And this is what we look like inside. What we're looking at. So this is the stator end. This must be the feedback, so the sensor unit. The wires on this winding do seem a little bit small, especially compared to any brushed motors I've looked at. They do seem like tiny little wires. But I know that the motors are lower current than brushed motors, so I don't really know what to think of that. The shaft will go all the way through the motor like that. It's this one here. So on the rear side here, we do actually have, these bearings are doubled up. So they're the same tiny little bearings, but we've got two on the rear and then one on the front. I think the front one is just pressed in from this end. So it might be possible to change this one out. But these ones here, to change them out, this looks like it is a fine thread nut on there, so you can take this off, but then this sensor you won't be able to remove, because what they've done is where it comes through the motor like this, they've epoxied all this in, so all the wires are stuck in place, you can't get them off, and then it looks like they've just soldered it in place. So this was done on the assembly level. So to get these bearings out, to change them, you'd have to desolder this sensor on there, which I don't think you're gonna be able to do without destroying it, to be honest. So at that point, this basically makes this a consumable unit. If anything breaks in here, you might as well just chuck it out, and that includes the bearings. So the windings are quite tight on here, which is nice. So one thing I have seen people do is they battle harden these by filling up all these little gaps with epoxy. The reason they don't do that at the factory is because epoxy is quite good at keeping heat in, so it's not great in terms of long life for your motor. But we're only ever running for 3 minutes, so heat shouldn't really be an issue. And it's more important that we keep everything in place and stop it sort of rocking about whenever we get some shock. So you don't want any of these windings to sort of fall this way and then get chewed up and short circuit. But these are quite tight, so I might not bother doing that part of the battle hardening. Ooh, except this bit here. See this little component just hanging off? I don't really like the idea of that. As soon as that gets a shock, that is liable to crack on there. So maybe we're epoxy on this board, but maybe leave the windings. Yeah, and there's 3 on each side. So there's 3 sensors there, and I'm going to guess that the number of magnets is not divisible by 3, and that's how they do the sense feedback. So whatever one of these is in line with the magnet should be able to feed back to the controller and tell it where it is in its cycle. So what we got? Let's start with this blue one. 14. So I'm right. Maybe. Right, well, let's look at this other bit anyway. So this outer can is made of 2 parts, you can see now. And what it looks like is this one. Let's do a little drawing. So this part here is actually keyed into this part here. So it's got a little shoulder on it like this. And the shoulder actually goes like this. So it's been heavily machined. And each of these slots kind of accommodates a magnet like that, so it gives a little housing to get the spacing correct. So that's the magnet, and that is the bottom part, and then the keys in, and then this outer can here is just a tube that goes around like that. So it's a lot of machining in there. It's quite nice as well. It's got like a little, where the shaft obviously goes through there, it's got a little boss, so a little piece like this, which is chamfered, which just helps support the shaft and gives you a little bit more engagement. That might be to help this, to prevent this shaft spinning in this can, so it gives you quite a lot more surface area engagement. So the motors are held in at the top with this kind of, it feels just like a really hard plastic, like a resin. It's going to be a high temperature plastic, I'd imagine, just to keep all the motors nice and square. And I guess that's why the epoxy or something sets to set them all in place. And then we've got this blue gunk on there, which is it's a really heavy epoxy. So it's to make sure the motor's balanced really well. And it just tunes the motor. Any imbalance in the motor would cause a lot of vibration, which would affect its use in its primary market as like hobby airplanes and things, where vibrations would cause quite a lot of issues. Like in our instance, it's not such a big deal, and actually what we're probably going to do is dump a bunch of epoxy in between all these magnets, just to make sure that they can't move and that they don't shatter so easily. So if you look at that, we're looking at really, really tight tolerances in there. Like, you can probably just about make that out. The magnets are nearly touching these stator windings here. So given that this is spinning really, really quickly, and it's very, very close to these stator windings, like I really wouldn't feel safe relying on just these tiny little bearings to prevent this from rocking about and maybe scratching the inside. I would think it's necessary to sort of build a whole bearing unit around this. So I probably would pick up on this, where the motor's like this, with that bit there, here. And the shaft goes through here for a mount face. We'd probably pick up on here with a bearing, and probably a bearing as well, and kind of link them together with a big sort of casing on the outside. At which point, like, by the time you do all this machining, like, how much weight are you really saving with the brushless? Like, the performance is going to have to be pretty good on these to make that worth it. We'll see. I'm keeping an open mind, we'll see, but initial thoughts is, I don't like it. They just seem like they're going to be a little bit fragile perhaps for our use, but if we've got the start off torque, if we can compare with the amp flows, like just look at the size of these compared to the amp flows, like these are tiny.
I do actually have an amp flow. I'm going to go grab it just to do a comparison. So here we go.
So yeah, it's kind of, yeah, weight saving alone, like this is going to weigh a fraction of this obviously. So just on the motors alone, we are looking at about a 2.3 kilogram saving. Even by the time you build up the sort of bearing housing, we're probably still going to save a bunch of weight on these. But it's just hard to believe that we're going to get the same sort of power as this from this. We will run an experiment. So what I'm going to do is we're going to compare the power usage and we're going to compare the start torque of these two, and we'll do a practical test, and that'll be in a coming video. But I'm not seeing it. I can't see how it's gonna compare. I just think that this one's gonna blow this one out of the water, to be honest. But I'd love to be surprised by this. This video isn't about the amp flow, so let's throw that one away. Let's draw this out. What I want for my model is I want something that's just going to be functional. I'm not looking at getting this 100% perfect and photorealistic, because that's going to be no benefit whatsoever. We already know that this is a non-serviceable item. So is there any point in drawing much of this on the inside? Like, is there any point in modelling up all this? The really important parts are the ones that are going to interact with other parts on the machine. All it does is it bogs down your computer with lots of different surfaces, and especially since we're using this motor a lot of times in the model potentially. By the time you finish a top level assembly, you're going to have sort of maybe 1,000 parts in there, and every surface does start to matter at that point. Right, so let's start with this one because it's easy. I want to model this in 2 parts. One possible modification I could see that we might end up doing is changing out this shaft for one that's a little bit longer and potentially doing something different with the retention method. Even if we don't do that, we still might change out the shaft just because, like, I don't know what material this made out of. That's something you really have to watch out for when you're getting things made overseas, is you just can't be sure of the material. And given that we can change this shaft and it's only 8mm, it's taking an awful lot of force. It might just be worth changing it just to be safe. So we'll probably change it for a EN36 or something, just a higher grade of steel that is traceable and is proven. So yeah, I'm gonna model this can in one part, and then I'm gonna model the shaft separately. We're gonna put them together in the top level assembly. So we'll end up with 3 parts. So we'll end up with this part, and this part here. So the way I do this is I kind of sketch out everything on paper first, get all the dimensions I think I'm gonna need, and then go to SolidWorks. And that way it just saves you having to go from the computer to calipers, It seems like it's a little bit more work up front, but it makes the modeling go so much quicker that it really does pay for itself. So let's start with this one here. And I'm going to draw it in the way I'm going to model it as much as possible. So we've got a center line on here. We can tell this is obviously going to be a revolve. We really need to model anything inside this. We could just make it a box, but I'm going to go into a little bit more detail just because, but it really doesn't need it. Can't get in there. So what I'm going to do is I'm going to zero off this ruler and chuck it on top. So this has been designed by someone. So when you get whole numbers like that, they tend to be right, because people don't tend to put in goofy dimensions. They try and stick to round numbers. That's probably about 4. Let's try and gauge this radius. It's not too vital. So it's probably about an R1. And then this shaft here. So this is the one we would pick up with a bearing if we're putting an external bearing on there. And then we got this shaft here. And then the same on the other side. I'm not going to draw a keyway. Each circlet groove should be to a standard, so we can check these against the, we'll have a chart from. So this one looks a little bit more daunting, but we're just going to focus on the bits that we actually want from it. So we're not too worried about, basically we're not too worried about here down. Like this is, I'm going to put this in just as kind of a cylinder, just to show the shape of it. The position of these wires are actually quite important as well, and the minimum bend diameter. So we want to make sure that where we mount this, we're going to be able to get our wires back through into our robot. And that's something that is often overlooked, and people end up having to drill holes last minute because they don't think about where the wires can actually bend. We are M4s. And a nice way to do this is you pick up the size of the hole, you zero it, and then you can go to the outside and you'll get an accurate read into the middle. The manufacturer probably has a drawing that shows this detail anyway, but again, I've learned not to trust that because I trusted it before and they were slightly wrong. Even if there are models for this that are available, you should probably still double check the dimensions, because sometimes they give you kind of simplified model that's got bits slightly wrong with it, or maybe it's a previous revision. If you're working with bad data, then it's not going to work in the real world. So I think that's about it. If I've missed anything, obviously I've got the part sitting in front of me, so I can just jump straight back to it. It's not always a luxury you have if you go out on site. Obviously you have to collect all the dimensions, otherwise you have to get back in the car. What I'm going to do is I'm going to get an overall dimension of the... To put this back together, it's going to snap. You don't want to let it go too quickly, otherwise it might damage the motor. Guarantee it's going to get my fingers, because there you go, back together. I'm just going to get some overall dimensions as well. And if these aren't correct, then we know we messed something up. So I guess the HA is the sensor bit, and then the C is the closed of that part number. The 63 must be the, what's 63 on it? The diameter, I guess. 74 is maybe the length. No, what's 74 on it? Nothing 74. I don't know. $5.30. Really gets caught on that burr of the keyway. Every time. There we go. They are nice motors. They seem just very. That bearing makes them very fragile, I think. And the floating electronics. If we sort that out, I think these are probably quite a good. Or if they've got the startup torque, I think that's probably a good way to go. And then you just need to seat them on there. You hit them clicking. Is Circlip a brand name? It might be. Cool. SolidWorks.
CAD.
It's like right in my way. I'm gonna have to figure out a different setup. CAD time. Sponsored by Extra Fiery Ginger Beer. No affiliation with Extra Fiery Ginger Beer. Oh wow, that really is extra fiery. It tastes like petrol. Kind of like it. That's okay. You may have noticed the outfit change. This is because the computer didn't save the first one we done, so I have to model it all again. So what we're going to do is I'll start off with the shaft, and then we'll do the can, then we'll do this stator mount face bit. The reason I'm starting with this one is not because it's the easiest. It's a little bit because it's the easiest. It's because I need the weight from it. So we're going to subtract that from the this can assembly, and then we can have an accurate weight for the can on its own. Maytech shaft. I'm going to put the part number in there as well. So I'm not going to go into the ins and outs of how to model. I'm not going to make this a tutorial. I'm going to try and keep to the sort of general ideas of modeling wherever possible. There are plenty of places you can go and actually learn how to use SolidWorks. We're going to have loads of CAD coming up anyway, so I don't want to start having to explain every single step because it'll just take forever. So select a plane there. And this is a turned part, so turned parts I tend to just do as revolves because that was kind of how it was made. Got a bunch of common features, so I'll try and tie everything together with the relations before we use any dimensions. More or less self-taught on SolidWorks, so I don't really know the names for a lot of stuff. I just know where they are. I use an awful lot of keyboard shortcuts. Okay, well, they're not. It does say fiery on it. They're not lying. So what you do once you're basically trying to tie everything back down to this point there. So this is the only point that's fixed when you start up a sketch. And as soon as you fix the components, they turn black. And a good test is you can't move them around anymore as well. So you just have a look, make sure nothing's blue. So there we go. So that is half of our shaft. And what you do is you pick that center line, go to evolve, and you got a full shaft. What's next? I try and keep radiuses till last because you might need to pick up on geometry in the sketch. And it ends up being a pain if you accidentally pick up on the corner of a radius and then you change the radius, it changes everything. Obviously change with it. So I'm going to do this not circlip. It's the keyway slot now. So it lives in the center here. So I need to pick up on that line, and then I can use that point as a center line as well. I'm doing exactly what I said I wasn't do. I'm trying not to get. I'm going through like a tutorial. So this was a nice dimension to measure because the calipers could get in there and open up. So that's why I'm going to the end of the slot to dimension it. I want to shut up now because it didn't work anyway. It was stupid. Oh, what an idiot! What happened? There's that one. I'm so good at SolidWorks. Look at me. You stupid. Right, stay where I put you. And then the depth, which I think was... I forgot the depth. Oh, my calipers are outside. Oh no. I was going to guess. No, I'm not going to guess. There will be a standard for this. I save me walking outside. Oh, come on, Firefox. You're embarrassing me in front of my internet friends. No, we want the slot, T1. 1.8, there you go. And we just assume that they've done theirs to standard. That looks about right. It does. It looks close. See? It's the same. It's the same. Same. Then one little radius, 0.5 on that top one.
Shaft.
We're done. Oh no, we're not done. Material is some kind of steel, and the weight is, the mass, 38.55 grams. So we're going to make sure we take that away from the 307 of the full assembly, because I couldn't be able to take it out. New part! And this is just the can, isn't it? Just call it a can. You know what that means. So let's do... That part there is the bottom. So it's another revolve. Obviously it's a motor, it spins around, so everything's going to be a turn part. Am I going to do this in 2 different parts? Yeah, let's do it in 2 different parts. So that is 4. That is... I'm going to shut up, otherwise I'm going to find it so hard to edit because I keep talking. SolidWorks does mesh for you, by the way, so if you can't be bothered to... If you're too dumb to do it yourself like me, you can just put it in there. Boom, part. Oh, I didn't put a hole in it. How are we going to get the shaft in? You silly goose. What are you doing? Now bush. And we're not going to merge them so they'd be 2 separate bodies, because we can give them different materials for what it's worth, but we don't need to. We're never going to take this part, this bit apart, so some kind of aluminium. We're going to change the weight anyway, so it doesn't really matter. That'll do. Anything else? Oh yeah, there's a radius. So what we want to do now is go to our mass properties, and everything's great. Everything we do at work is kilograms, because we do massive steel work usually. It's very rare that we do stuff small enough that grams are going to matter. What we're going to do is change the mass properties to our 307 minus our 38.55, which was our shaft. Second part done. And this was the Maytech face plate. Surprise, surprise, it's a revolve part, so it's going to get a revolve. Okay, we've got to do the holes up on top now, so I'm just going to use this hole wizard. And they were M4s. We're going to do 1 hole, and then we're going to pattern it around, revolve pattern it. The computer's really struggling. I can't tell why, because there's nothing open. It's because it's too open, that's why. Yeah, SolidWorks is just fun sometimes. I have no idea what's up with this computer. It's really, really struggling. Okay, now we just got to do this weird little indent thing. And there we go. One more thing I want to do is I just want to put in the leads and show the minimum bend radius. Just sometimes you end up having to put stuff in close proximity, and you just want to make sure the leads can actually bend round and fit into holes and stuff like that. It's something that's caught me out before, so I just try and do it on all my models now. So what's the best way to do this? I kind of want them to go down, I guess. So I'll do I want them to come out this way. So I'll do 1 and then pattern it over. So we need a plane. God, I'm really making a meal of this. Is that about right? No, because we don't need that. Yeah, we will need that. Okay. Let's hide all these. They're just getting in the way. That's just the distance you can bend the wire before it starts kinking and being a problem. Silicon wires are quite vulnerable to being split as well. So as soon as you get a tiny little cut in them, as soon as you bend them too far, it just opens up, and then we'll have all sorts of problems with wires shorting out and whatnot. Right, so we got our two, and we sweep it. There you go. It's a wire, and I just want to pattern this. So let's find a surface that goes that way. One of these planes must. There's tons of them. Boom! I'm going to say is that part done? It's everything important on it, isn't it? So I'm going to say that's part done. Part done. Time. We're going to make an assembly. So what I want to do is I want to start with my can first, because I know that isn't going to change. Whereas the shaft, we're gonna make a configuration. Oh yeah, I didn't tell. We're going to make a configuration to turn the shaft on and off, so that if we dump the model in and don't want to use the shaft, we can just take it out without having to go in and edit the model. So we only have one model floating around. We don't end up with a bunch of them that we've changed bits of, and then there'll be weights all over the place. And oh, I forgot to do the weight on the other part. That'll do. Right, now to the what we're doing, assembly. Right, so we got our can in there. Let's put the shaft in. Oh, that's what else we didn't do, and we didn't do the grub screws as well. I swear I'm good at this. I swear this. If you hire me, I swear I'm good at this. It's fine. There we go. Got a little hole in there. Hide that plane because it's ugly. And then we're gonna do a revolve around 120, just like it never happened. And just got to dump in this part there. Oh. And we've got a dimension that we took of the assembly from the top to the bottom. 69. And there we go. And I'm going to put in a toolbox part as well. So I'm going to put in this circlip, just because we will actually have to mind out for that. Because when we're mounting to it, obviously we want to give enough clearance so that this can spin and it doesn't clash. And I think with that, and I think we're done. I think that's. I'm gonna export this out as a parasolid and a step, so they're both neutral files that everyone should be able to pick up and work with. And I'm gonna put that. Oh no, configuration. We didn't finish. Derived configuration, and we're gonna call it shaftless. Suppress that part there. And that's going to fall off because I'm an idiot. So rather than have that mated to the thing, let's do it to the outside. What a donut, huh? Fixed it now though. Whatever. We're going to have to hide that circlet because obviously it's just going to float about as well. And we can go between that one and that one. And this shaft comes off, shaft comes off, shaft comes on, shaft comes off, shaft comes on. Right, start again. So I'm going to export this as a step and a parasolid, and I'll put it up on my website. If you use it and it don't work, I take no responsibility for that. That's your fault. You should have checked it. I checked it. ESC next. Thanks. Subscribe.